From rugged dirt paths to modern superhighways, roads are one of those consistent background characters in nearly every person's story. And if you've ever been a driver, I know a similar character in your life, road construction. Most of us love having wide, smooth roadways to take us to work, to home, and everywhere else we travel, but we're hardly ever excited to see a construction project starting on our favorite roadway. I'm here to change that, or at least to try. I love construction, always have, and when it happens along my commute, I love it even more because I get to see the slow but steady progress each day. And I think, or at least I hope, that if you can know a little bit more about what's going on behind those orange cones, you might appreciate it a little more as well. So I'll start with step one, and if people are interested, I'll keep the series going. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about earthwork for roadways. This video is sponsored by Brilliant. More on that later. The first roads in history were probably formed as people or animals followed the same trail long enough to tamp down the vegetation and establish a route between 2 points. But that's not enough for the roads of today. Why? Because the Earth is full of irregularities that aren't conducive to safe, efficient, and convenient travel. There's a reason we have the distinction of off-road vehicles. ATVs and dirt bikes are fun, but most of us don't want to wear a protective bodysuit for our daily commute. Safe and efficient travel means smooth curves, both horizontally and vertically. It means grades that aren't too steep, and it means paths that are relatively direct between points of interest. In a very general sense, that means to build a roadway, we need a way to smooth out the surface of the Earth. A lot of people use words and writing to communicate, but roadway engineers and contractors use the cross-section. This is a special kind of drawing that shows a slice through a particular location, and it's the literal language of road building. On it, you can see the level of the Earth before construction and the proposed surface afterwards. Any difference in these two lines means some earthwork is going to be required. Areas above the proposed roadway need to be excavated away, also called cut, and areas below the proposed road need to be filled in. Cut and fill are the most fundamental concepts in any earthwork project, and keeping the cut and fill in balance with one another is a critical part of roadway engineering. After all, if you need to fill in some areas, that soil is going to have to come from somewhere. Rather than importing soil to a project, it makes a lot more sense to take it from somewhere that already needs it removed. And if you're going to have to excavate tons of soil from some part of your project, it sure would be nice if, rather than having to dispose of it, you could take it to some other part of your project that needed additional material. If the amount of cut and fill on a project is balanced, every shovelful of dirt is doing two jobs: taking soil away from where it's not needed and gathering soil for where it is. So engineers designing roadways keep track of these quantities between each cross-section. Of course, earthwork may seem simple when you're just looking at a drawing, but here are a couple things to keep in mind. Soil is heavy and roads are long. Just because you have the same volume of excavation as you have fill doesn't necessarily lead to efficiency, because if all the cut is miles away from all the fill, you're going to have to make a lot of trips. So roadway design not only needs to balance cut and fill, but also to try to minimize the haul distance. Mass haul diagrams show the net change in earthwork volume over the length of the roadway. This gives the pros a quick understanding of the amount and distance of earthwork for an entire roadway project. But we're still not there yet, because once you get all that soil in the right place, you can't just build a road on top. I've said it before and I'll say it again, soil's not that strong, especially in loose piles fresh from the bed of a dump truck or scraper. We have to compact it down. But even that's not so simple. There may be no other material more tested than soil. Maybe blood, but if you measure by weight, I don't know. In testing labs all over the world, probably at this very moment, there are people looking at and taking pictures of, shaping and rolling soil, inserting it into equipment, taking measurements and writing those measurements down on clipboards. Why? Because soil is really important. The cost of building roads varies from place to place, but very roughly, it's about $3 million for a mile of two-lane roadway. That's about $2 million for a kilometer. Roads might be the most expensive thing you touch on a typical day because they take a lot of work and a lot of material to build. So if we're going to go to all that expense just to make it easier to drive our cars from place to place, we need to make sure that the roads we build have a good foundation. That mainly means proper compaction. Soil settles and compresses over time, and if this happens with something on top, like a road or any other structure, it can lead to damage and deterioration. Compaction speeds up that settlement process, so it all happens during construction instead of afterwards. If soil is compacted to its maximum density, that means it can't settle further over time. But how do we know whether it's compacted enough? That's where the testing comes in. Soil labs do a ubiquitous analysis called a Proctor test. If you add different amounts of water to soil and try to compact it, you'll see you get different densities. With low moisture content, it's nearly impossible to do any compaction. Same thing with high moisture content. But somewhere in the middle, you'll get the maximum density. This estimate of maximum density is one of the most crucial measurements in earthwork. Soil used for filling areas is first placed in roughly the correct location by a dump truck or a scraper. Then it's smoothed into a consistent layer called a lift by a bulldozer or motor grader. Finally, each lift is compacted using a compactor. This is at the heart of why earthwork takes so long to complete. You can't compact soil more than around a foot at a time. That's 30 centimeters. Rolling over thicker layers will only compact the surface, leaving the rest free to settle over time. So areas of fill, and especially tall embankments like the approaches to a bridge, need a lot of individual layers. By necessity, they come up slowly, little by little, lift by lift. Every so often along the way, someone does a test to check the density of the compacted soil. There are a few ways to test density, but we mostly use nuclear gauges that measure the radiation passing through the soil to estimate its degree of compaction. We compare that measurement with the maximum density measured in the lab. If it's close, it's okay. If not, we keep compacting until it is. That gives engineers and contractors the confidence that when the roadway surface is placed, it's going to be there to stay. But it's one of the biggest reasons that roadway projects take so long to complete. We can move a lot of earth quickly, but to place and densify it into a foundation that will stand the test of time is a process, and it doesn't happen right away. One last thing I want to point out, during the construction of a roadway, or really construction of just about anything, this earthwork causes a lot of disturbance. What used to be grass, plants, or some other type of covering over the ground is now just bare soil. That may not seem like a big deal, but to all the aquatic wildlife in nearby creeks and rivers, it is. That's because anytime it rains, all that unprotected soil gets quickly washed away from the construction site into waterways, where it reduces the quality and quantity of habitat. So pretty much every construction site you see should have erosion and sediment control measures in place to keep soil from washing away. Mulch socks and silt fences slow down runoff so the sediment can drop out, and rock entrances knock most of the mud off the tires of vehicles before they leave the site. Like it or not, roads are a part of the fabric of society. Travel is a fundamental part of life for nearly everyone. Unfortunately, that means road construction is too. But I hope this video gives you a little more appreciation for what's going on behind the orange cones. You know that metaphorically significant planar surface where the rubber meets the road? Well, it couldn't even exist without the engineers and construction workers designing and building the planar surface just below, where the road meets the earthwork. You may have noticed in the video that earthwork is really just a problem in geometry, using excavation and fills to literally reshape the earth. People who excel in spatial problem solving make great civil engineers and contractors because geometry is needed for nearly every step of design and construction. Today's sponsor, Brilliant, is a problem-solving website that teaches you to think like an engineer by taking topics like geometry, breaking them into concepts, and guiding you through problems to build your knowledge and intuition. Anyone can read a textbook or watch a few videos. Brilliant takes learning so much further by making courses interactive and thought-provoking. I've been using Brilliant for several years now, and it's been really exciting to see them add new courses and features with a focus on great design. Have you ever seen search results this beautiful? Sign up completely free and let them know you came from this video by using brilliant.org/practicalengineering. The first 200 people that use the link will get 20% off the annual premium subscription. Thank you for watching, and let me know what you think.